Okay. So today we're gonna solve shortest path in undirected graph. So you're given an adjacency list of undirected graph having unit weight of edges. Find the shortest path from source to all vertex, and if it's unreachable to reach any vertex, then return -1 for the vertex. Okay. So we are given an adjacency list. Zero comma 4. Okay. So this is how. This is what we are given. So what is given is from node 0 we have an h2 1 comma 3. From node 1 we have an h2 0 comma 2. From 2 we have an h2 1 comma 6. From 3 we have an h2 0 comma 4. For 4 we have an h from 3 comma 5. From 5 we have an h2 4 comma 6. From 6 we have an h2 2 comma 5 comma 7 comma 8. From 7 we have an h2 6 comma 8. From 8 we have an h2 7 comma 6. Okay, let us draw a graph, and it's an undirected graph. So node 0 to 1 we have a path. Node 0 to 3 we have an h, and from 1 to 0 we already have an h. From 1 to 2 we have an h. From 2 to 1 we already have an h. From 2 to 6 we have an h. 3 to 0 we already have an h. So 3 to 4 there's an h. From 4 to 3 we have an h, and 4 to 5 we have an h. 5 to 4 we already have an h. From 4 to 6 we have an h. 6 to 2 we have an h. 6 to 5 we have an h. 6 to 7 we have an h, and 6 to 8 we have an h. 7 to 6 we have an h, and 7 to 8 we have an h. 8 to 7 we have an h, and 8 to 6. Okay. This is the graph that we get after from this adjacency list. So now what we are supposed to do is we are supposed to find the distance from source to all the other vertices. So as it's a unit weight graph, we'll have a weight of 1 on all the edges. For finding shortest path from the SRC, we use Dijkstra algorithm, which basically says is if u is the distance to the node from the source node and v be the cost of the node, v be cost of the node, which here is 1, is less than the distance of the node v, then distance of node v is gonna be v plus v. Okay. This pretty much sums up what we are gonna do. So here, let us first solve this using breadth first search method. Breadth first search method, right? So let us take a queue and here we have our source index as 0, right? So for the source index, that is node 0, the distance or the path cost is gonna be 0. So what we are gonna do in the queue is we are gonna push node and cost inside the queue. So here first we're gonna push node 0, that is the source node, and it has cost 0, so it's gonna be 0, 0, 0. And before that, let us initialize an array, a distance array, for tracking the distance of all the edges when we are visiting from the source node. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and let us initialize all of them as infinity, as we haven't visited any of these nodes, so let us keep it as infinity, right? So since we pushed it into the queue, and here u plus v is gonna be 0, as it has no path passed, and this is a source node, so this is 0 and this is 0, and this is less than distance of node 0, that is infinite. So we're gonna change this to 0. Next we're gonna push its neighbors, that is 3 and 1. So it's gonna be 3, 1, and 1, 1. Okay. So now we have 3, 1. The path cost is gonna be 0 plus 1, that is less than distance of 1. So this is gonna be changed to 1. Sorry. Similarly, this is gonna be changed to 1. Okay. Now, if we are gonna pop this out and push neighbors of 3. So the neighbor of 3 is 4, which is not already visited. So we're gonna go to 4. 4, 1. So this is gonna be 1 plus 1 is less than distance of 4. So this is gonna be changed to 2. And similarly, while popping this out, we're gonna change the distance of 2 to 2. Let us push it inside. 2, 1. Right. Now we're gonna pop out 4, 1. So while popping out, we'll insert its neighbor, which is 5. And for 5, we have distance till 4 as 2. So 2 plus 1 is gonna be 3, which is less than infinity. So we're gonna change this to 3. Right. And then we're gonna pop 2, 1, which will lead to 6. Right. So the path is gonna be 1, 2, 3. Now we're gonna pop out 5, node 5. So node 5 will give us path to 6, basically. But if we are coming from 5, then we'll see that the weight is gonna be 1, 2, 3, 4. Via this path, the distance is gonna be 4, but via this path, the distance is gonna be 3. As distance of 3 is less than distance of 4, the distance of node 6 won't be updated, right? Now we are gonna pop out node 6 and we'll insert 7, 1 and 8, 1. Right. 7, 1. So 3 plus 1 is gonna be 4, less than infinite. So this is gonna be changed to 4. this is gonna be changed to 4. So our answer is 0, 1, 2, 1, 2, 3, 3, 4, 4. Right. So which is pretty much what we needed. Right. So we're gonna use BFS algorithm for solving this question. So let us code this up. We have a distance matrix. INF. Let us declare what INF is. Int max regions. Okay. We initialized distance matrix. Now what we're gonna do is we're gonna initialize Q we're gonna keep it as a pair, as we're gonna store node comma cost. Here actually we don't have to save this up because the distance is unit cost. So what we're gonna do, just for the sake of space complexity, we're just gonna store just the node. Right. Well, Q is not empty. Okay. So yeah, BFS along with Dijkstra. Now what we're gonna do is we have the array, so it's gonna be something like, for suppose we didn't find any path to a particular node, so then it's gonna be 0 comma inf comma 0 comma 3 comma 4 comma 5 or something like that. So if we didn't find any path, then we are gonna have inf, because that's what we initialized the entire distance array with. So what we're gonna do is we're gonna replace inf with -1, right? For unreachable vertex or vertices, let's say. So for or let us take it as the index form only. I is equal to 0, I is less than. We're gonna return distance. Let's see if it's working. Optimizing our code. Oh yeah, we forgot to pop it out. Sorry, this should work. We again have a compilation issue. Why? Mm, I think maybe it's taking a lot of time because we are using BFS. Let us see what exactly is gonna be time complexity for this solution that we have here. So here we're gonna traverse all the nodes. This is gonna be order of n, and this is gonna be So here the each order of v plus e, as we're gonna um, visit each vertex once and each edge one. So it's gonna be order of v plus e. I don't know why are we getting the error. Maybe because we are supposed to use a priority queue. What the hell? Um, yeah, yeah. So this is a solution. We're gonna push the node after we process the distance instead of put it outside, which leads to inefficiency. That's the reason it was giving us time limit error, but now it's working fine. So this is how we're gonna do it. Right.